More examples of being able to evaluate trigonometric integrals. This one's going to be our 3 cosine to the 5th power of 1/2 x dx. To be able to start this one, you'll note that there's no reduction for the cosine to the 5th, nor is there any sort of Pythagorean identity that we can use because it's not even an even power. And so here's a way to try to approach this one. Start by factoring the 3 out and breaking off one of the cosine functions. Okay, so I'm going to have cosine to the 4th of 1/2 x times cosine of 1/2 x dx. Now, another way to think about that cosine to the 4th is to think of it as cos squared squared. And that's exactly what we're going to think of it as. So this is going to be 3 integrals of cosine squared of 1/2 x squared. And then we have our cos of 1/2 x dx that's sitting on the outside. The good news is now we can use a Pythagorean identity on this cos squared. And now we can rewrite this as 3 integrals of 1 minus sine squared 1/2 x, still quantity squared, times cos of 1/2 x dx. And the whole purpose of this is to be able to do a u substitution, because we know that the derivative of sine 1/2 x is going to give us 1/2 cos of 1/2 x. And so at least we can start to get rid of that cosine that's on the outside. So let's let u be equal to our sine, just the sine, not sine squared, of 1/2 x. The derivative, by using our chain rule, is going to be 1/2 cos of 1/2 x dx, which is good because that gives us all of this. Okay, but we don't like that 1/2, so we're just going to multiply by 2 on both sides. And 2 du is going to be cos of 1/2 x dx. And now that gives us the substitution that we want solely in terms of u and du. We're going to carry the 3 down. So we have 3 integrals, quantity 1 minus u squared, since we said u is equal to the sine of 1/2 x. And then we have this 2 du that we're going to substitute for the cos 1/2 x. So it's going to be times, and this is squared, by the way, times 2 du. Now what I'm going to do, I'm going to factor the 2 out, okay, and multiply it by the 3 to get 6. I'm also going to expand this 1 minus u squared squared. And so this is now going to be 6 integrals. Now, when we FOIL this out, remember, 1 minus u squared squared is not going to be 1 plus u to the 4th, okay? Instead, what we're going to do is we're going to turn it into a FOIL problem. And ultimately, it's going to end up being 1 minus 2u squared plus u to the 4th. And we got rid of the 2 as the coefficient or the factor, and there's a du. Now we can integrate term by term. So this is now going to be 6 times u minus 2u cubed over 3 plus u to the 5th over 5 plus our constant of integration c. And now finally, we can distribute the 6 and back substitute. So we're going to end up with 6. Remember, the original substitution was sine of 1/2 x. Okay, so everywhere we see a u, we're going to have a 1/2 x. This is going to be 6 times sine 1/2 x minus, that's going to be 4. Well, we multiply 6 times 2 is 12. 12 over 3 is going to get us 6. And we have sine cubed of 1/2 x. And then finally, I'm just going to drop to the next line, 6/5 of sine to the 5th of 1/2 x plus our constant of integration c. All right. Be wary when you're checking these if you use a computer algebra system, such as like Wolfram Alpha or Symbolab. A lot of times with the trigonometric integrals, it's going to give you a very strange sort of answer. All right. And that's because the computer algebra systems either use a different algorithm or they try to simplify things by using strange or let's say unique trigonometric identities. All right. One more example of a higher order sort of sine function, and this could be applied to cosine as well, is sine to the fourth. All right. Now, this is a traditionally ugly sort of one, but we can use the same technique that we just saw by writing this as sine square of x square dx. And the reason this one's a little bit nasty is because we have to use the power reducing formula within this one, right? So now remember, our power reducing formula is going to say 1/2 minus 1/2 cos of 2x, but that's still squared dx. Okay, so we just dropped down this square, and then the sine x became all of this by our power reducing formula. Now we can expand the square. All right, so now this is where it starts to get a little bit ugly. All right, so we're going to multiply this out. Okay, so think of it like a FOIL problem. Okay, so it's 1/2 minus 1/2 cos 2x times 1/2 minus 1/2 cos 2x. All right, so don't forget that this is a FOIL problem when we're doing it. So our new integral is going to become 1/4. We're going to have 2 of those 1/4 when we multiply the cosines. So it's going to end up being 1/2 cos of 2x. And then this is the one that's really going to get us, is we are going to have a positive 1/4 cos square of 2x dx. All right. So these two first terms are easily integrable. Okay, we can find an antiderivative for both of those rather easily. Unfortunately, this 1/4 cos square of 2x is not basic. And so what we're going to have to do is we're going to have to use the power reducing formula again on this. Okay, and so we're going to keep our constant of 1/4. We're going to keep that 1/2 cos of 2x. And now we have our power reducing formula. And remember, the power reducing formula for cosine square is going to be 1/2 cos, or 1/2, excuse me, plus 1/2 cos of, now be careful here, 2 times 2x. All right. And remember, when you're doing the power reducing formula, you have to double that interior angle, just like we did initially, right? We had sine of x, and when we used the identity, we doubled the interior angle. And so clearly, this is going to turn into a cos of 4x. All right, now we're going to clean this up. Okay, so what we can do now is clean this up, and we notice that we have a 1/4, and this is going to be 1/8. Okay, so the 1/4 and the 1/8, we're going to add those together to get 3/8. We still have the negative 1/2 cos of 2x. And then finally, we have 1/4 times 1/2, which is going to be 1/8. And that's going to turn into cos of 4x. Okay, so that's going to be 1/8 cos of 4x. And we still haven't taken an antiderivative yet. We're getting there. Now, mercifully, we can finish this off because now all 3 of the components are easily evaluable. And so if we integrate with respect to x, the first one's just going to be 3/8 x, no problem there. Because we're taking an antiderivative of cosine, we're not going to multiply by this interior 2, but we're going to divide by it. So it's going to be 1/2 times 1/2 sine of 2x. And then similarly, because we have an interior function of 4x, and we're taking the antiderivative of that, that's going to be 1/4 sine of 4x. Just enough room to plug in a constant of integration. And now finally, we can write our final answer, okay, or one form of it. So it's going to end up being 3/8 x minus 1/4 sine of 2x plus 1/32 sine of 4x plus our constant of integration c. Right? So a little bit sneaky on that one, but if you ever have a power of sine or cosine, that's even, and you just have the sine or the cosine by itself, this is the technique that you're going to have to use. Okay, so you're going to have to basically write it as a quantity squared or something cubed or something to the fourth, hopefully not to the fourth, and then just use your power reducing formula. And you might have to use it a few times to be able to get to your answer. All right, so in our next video, we're going to take a look at one last sort of sine and cosine problem, how to integrate. And then we're going to move on to our secant and tangent pairings.